What if I told you the moon is the only reason Earth isn't a chaotic hellscape? Right now, the moon stabilizes our planet's tilt at 23.5 degrees. That tilt gives us spring, summer, fall, and winter. Predictable, stable, safe. But the moon is drifting away. And as it does, that stability weakens. Without the moon, Earth's tilt could swing from 0 to 85 degrees over millions of years. 0 degrees means no seasons. The equator boils, the poles freeze. 85 degrees means the North Pole faces the sun for half the year. Imagine 6 months of daylight, then 6 months of total darkness. Nothing survives that. And the moon's escape is already in progress. Right now, while you're watching this video. So why is the moon leaving? And more importantly, what happens when it gets too far? Let me show you the evidence. In 1969, Apollo astronauts placed mirrors on the moon's surface, not for decoration, for measurement. Scientists have been bouncing lasers off those mirrors for over 50 years. Every pulse of light travels to the moon and back, allowing researchers to calculate the exact distance down to the millimeter. And the data is undeniable. Every single year, the moon moves 3.8 centimeters farther from Earth. That's about the width of 2 fingers. Over a human lifetime, that's barely a meter. But over millions of years, that tiny drift becomes catastrophic. Because the moon isn't just a light in the sky, it's Earth's gravitational anchor. And without it, our planet becomes unstable. So what's causing this? The answer is tides. But not in the way most people think. The moon's gravity pulls on Earth's oceans, creating bulges of water on the side facing the moon and the opposite side. That's what causes high and low tides. But here's where it gets interesting. Earth rotates much faster than the moon orbits. Our planet completes 1 full rotation in 24 hours. The moon takes 27 days to circle us. Because of that speed difference, the tidal bulge doesn't point directly at the moon. It gets dragged slightly ahead by Earth's rotation. And that forward-facing bulge creates a small gravitational tug on the moon. Instead of pulling it closer, it pushes the moon forward in its orbit. And in orbital mechanics, when something moves faster in its orbit, it gains energy. More energy means a higher orbit. A higher orbit means farther from Earth. This process is called tidal acceleration, and it has been happening for 4.5 billion years. When the moon first formed, it was terrifyingly close to Earth. So close that it would have filled nearly half the sky. Imagine looking up and seeing a massive sphere looming overhead, hundreds of times larger than the moon appears today. Tides back then weren't gentle waves. They were colossal walls of water that reshaped entire coastlines. And Earth didn't rotate slowly like it does now. A single day lasted only 5 or 6 hours. The moon's gravity has been gradually slowing Earth's rotation ever since. Every century, our days get roughly 1.7 milliseconds longer. That's imperceptible to us. But over hundreds of millions of years, it adds up. Dinosaurs experienced days that were about 23 hours long. In another 200 million years, a day might stretch to 25 hours. The moon is stealing Earth's rotational energy, and in exchange, it's drifting farther and farther away. So what does the future hold? Will the moon just keep drifting until it disappears completely? Not exactly. Eventually, Earth's rotation will slow enough to match the moon's orbital period. At that point, both bodies will be tidally locked to each other. Earth will show the same face to the moon at all times, just like the moon already shows only one face to us. But that scenario is billions of years away. Long before that happens, the sun will expand into a red giant and engulf both Earth and the moon. So we won't be around to see the final chapter. But there's a much closer consequence, something that affects us right now: total solar eclipses. The moon and sun appear almost exactly the same size in our sky. That's not a coincidence. It's a temporary cosmic alignment. And as the moon drifts away, it appears slightly smaller every year. In roughly 600 million years, the moon will be too small to completely cover the sun during an eclipse. Total solar eclipses will become impossible. We are living in the only window of Earth's history where they look this perfect. That alone is remarkable. But the real danger isn't eclipses. It's climate stability. The moon doesn't just create tides, it stabilizes Earth's axial tilt. Right now, our planet tilts at 23.5 degrees. That tilt is what gives us seasonal variation. Summer in the northern hemisphere, winter in the southern. Then it switches. Without that tilt, the equator would receive relentless heat year-round, while the poles remained frozen. But the tilt itself would be fine if it stayed constant. The problem is, without the moon, it wouldn't. Computer simulations show that without the moon's stabilizing gravitational influence, Earth's axial tilt could vary wildly. It could drop to nearly 0 degrees, eliminating seasons entirely, or it could swing all the way to 85 degrees, creating extreme and uninhabitable conditions. For comparison, Mars lost any stabilizing influence it might have had billions of years ago. Its axial tilt swings chaotically between 10 and 60 degrees. That's one reason Mars is a frozen desert, with a razor-thin atmosphere. Earth could follow a similar path. Not tomorrow, not in 1,000 years, but over deep time, as the moon continues its slow retreat, our climate shield weakens. There's another subtle effect most people don't realize. As Earth's rotation slows, the length of our day increases. That might sound trivial, but it has real consequences. The circadian rhythms of living organisms are tuned to a 24-hour cycle. Plants, animals, even bacteria have evolved to function within that rhythm. If days gradually stretch to 25 or 26 hours, ecosystems would need to adapt. Some species might handle the shift, others might not. Over geological timescales, this could influence evolution itself, and it's already happening. Fossil records show that ancient corals grew daily and yearly growth rings, just like trees. By counting those rings, scientists have determined that 400 million years ago, a year had roughly 400 days. That means each day was shorter, around 21.5 hours. Earth has been slowing down ever since, and the moon has been moving away. So is there anything we can do to stop it? In short, no. Tidal forces are fundamental to orbital mechanics. As long as Earth has oceans and continues to rotate faster than the moon orbits, this process will continue. We can't reverse gravity. We can't halt the energy exchange between Earth and the moon. We can only observe, measure, and understand. And in a way, that makes it more profound. Because this isn't a crisis. It's not a countdown to disaster. It's simply the natural evolution of a planetary system. The moon has been our companion for over 4 billion years. It shaped our tides, stabilized our climate, and made life on Earth possible. But nothing in the cosmos is permanent. Not even the most familiar objects in our sky. The next time you look up at the moon, remember this. You're seeing something that won't always be there. Not in the same place, not in the same form. It's drifting away, slowly, inevitably, and beautifully, following the cold, elegant rules of physics. And in that slow departure, we see a reminder of something bigger. The universe doesn't stand still. Everything is in motion. Everything is changing. We just live on timescales too short to notice. But science lets us measure what our eyes cannot see. And what it reveals is both humbling and awe-inspiring. The moon is leaving. Not because it wants to, but because it must. So what do you think? Is this just the natural rhythm of the cosmos? Or should we be more concerned about what happens when the moon drifts too far? Let me know your thoughts in the comments. And if you want to explore more mysteries of our solar system, hit subscribe and turn on notifications. Because the universe is full of secrets, and we're just beginning to uncover them.